Hello, and welcome back to the Cracking FAANG YouTube channel. Today we're going to be solving a really popular Google interview question, Leetcode 2096, step-by-step directions from a binary tree node to another. Let's read the question prompt. You are given the root of a binary tree with n nodes. Each node is uniquely assigned a value from 1 to n. You are also given an integer start value representing the value of the start node s, and a different integer dest value representing the value of the destination node t. Find the shortest path starting from node s and ending at node t. Generate step-by-step directions of such path as a string consisting of only the uppercase letters left, right, and u. L, R, and U, sorry. Each letter indicates a specific direction. Left means go left, right means go right, up U means go up to the parent node. Return the step-by-step directions of the shortest path from node S to T. So if we were given this tree here, and we were told to start at 3, and we were told to end at 6, what's the shortest path? Well, we would start here, and we go up to the 1, up to the 5, we go to 5's right to the 2, and then we go to the left to the 6, which is the shortest path. So we would return up, because we went up to the 1, up to go to the 5, we went right to go to the 2, and then left. So that's going to be how we got UURL. So now that we've seen that, let's think about how we might solve this problem. Okay, so we read the question prompt and we looked at an example. Now it's time to figure out how we're actually going to solve this question. And this question follows a very common Leetcode pattern where you want to use a tree, but you need to represent it as a graph. So obviously when a tree is given to you, it's going to be in the format of like a tree node object, which has a value and has optional left and right pointers representing the left and right subtree. But in this question, we're told that we need to be able to go up, which means that, we need access to the parent, which our class doesn't have. Now, you could modify the tree node class to have a pointer to its parent, but it's already defined for you. So typically your interviewer is going to be like, no, you can't just add a field for the parent. So in this case, what we want to do is we actually want to transform our tree into a graph representation of a tree. And the way that's going to look like is going to be a dictionary where for each node, we're going to, have a list of all of its, nodes that it can touch. So for example, this 2, that would be the key, and then its values would be the node 5, the node 6, and the node 4, because those, 5 is its parent, 6 is going to be its left, and then we're going to have the right as 4. So that way we would have access to all the nodes that you can visit from 2. Now, this problem is unique in that it asks for the directions, which means that we have to keep track of the path that we've gone. So instead of just storing the nodes that we can reach from any given node, we also have to store the direction where that node is. So for the 2, again, we would store 5, but we also need to store U to indicate that it's the parent. When we store 6, we need to store 6, and we need to make note that it's its left child. And when we store 4, we need to store it with the right child. And we can do this for every single node in our tree. And then what we want to do is, since this asks for the shortest path, and we're working with a graph here, that should immediately scream to you that we want to do a breadth first search, starting from this node and trying to get to, our destination. And obviously a breadth first search in an undirected graph like this will give us the shortest path possible. So we can be sure that starting from our start node 3, that when we hit 6, that will be guaranteed to be the shortest path. So all we have to do is basically just traverse our tree and get to the destination node that we want, and we'll be done. So the way that we're going to do that is we're just going to kick off a breadth first search here. And remember, for 3, let's, think about what are all the options that 3 has. In this case, it doesn't have a left child and it doesn't have a right child. It just has a parent. So its parent would be 1. So we would traverse to 1, and, our current path would just be up. Then from the 1, we have the options of going to, 3, its left child. It doesn't have a right child, but we could go up to the 5. Now, remember, we don't want to go back to the 3 because if we did that, we would get caught in an infinite cycle. So we're going to need some sort of scene set to keep track of the, elements that we've been at, so we don't get caught in an infinite loop. So that means that, we're going to have to put 3 in here. So when one is deciding which of its, paths to take, obviously we can avoid going back to 3, because then we'll get caught in an infinite loop. So our only option is to go up to the 5. So we go up to the 5, which means that we go, to the U here. So let's see if we have extra space here. So the 5, what are its elements? Well, we could go, to the 1 to the left, but we know that this isn't possible because we've just visited 1, so we're not going to consider it. We could go right to its to the node 2, and it actually doesn't have a parent node because 5 is the root of the tree. So our only option is to go to the 2. So we go to the 2, which means that, we've taken a right. And now, okay, let's go to the 2 here, and we're going to say, okay, what are its options? Well, 2 can go to the 5 up, but remember, we just visited 5, so that means that 5 is not going to be available to visit because we've already been there. And we could go, left to the 6, or we could go right to the 4. So that we can do both of those options, and we'll have to try both because we actually don't know which direction to go. We have to try all the possible options. So we'll go to the left subtree first. So we'll go to the left, and we'll end up at the 6. And actually 6 is our answer. So we got there, and then we would just return UURL because that's the path that we did so far. So we're going to have to keep track of, the current node that we're at during the BFS, and also the current path that we've seen so far. So that way, when we reach our target node, we can simply return the path so far. So that's going to be the approach that we want to take to solve this problem. It is a little bit complicated if you've never seen this format of taking a binary tree, transforming it into a graph, and then traversing that graph in like a standard graph traversal. But once you watch my code for this, it should be a lot clearer, and you can use this pattern for a lot of questions on Leetcode because this is something that comes up quite often. So that being said, let's go into the code editor and actually write the code for this problem. Okay, we're back in the code editor. Now let's write the code. Remember that we're going to first need to represent our tree as a graph. And to do this, we're just going to do a standard, level order traversal through the tree to basically just populate our graph. So let's first define the data structure that's going to represent our graph. So we're going to say graph is going to be a dictionary whose key will be the node that we're visiting. So each node in the tree, and then its value will be a list of all the nodes that we can reach from that point. And remember, those nodes are going to be accompanied with the direction that they're at. So that would be the graph. And we need a queue to basically do the BFS traversal through the tree the first time to build the graph. So we're going to say queue, and we're going to define a queue here, and we're simply going to initialize it with the root. And now it's time to go through the tree to basically get all the elements. And we're going to do this in just a standard breadth first search level order traversal. I do have a video on how to do this. If you are a little bit confused on how to set this up, this should be something that you have memorized. You should know how to do a level order traversal without even thinking about it. It comes up so much in Leetcode questions, and if you are a little bit confused on how to do it, or it doesn't come to you immediately, you need to memorize this. This is one of those things that you need to have at the top of your head because it comes up so much in these interviews. So don't sleep on this. Don't be like, oh, I can just figure it out. No, you need to just, need to know exactly how to do it at the drop of a hat. So that being said, let's go through our BFS here. So the first thing that we do is we pop a value from the queue. So we're going to pop left from the queue to get a node. And now what we want to do is if that node has a left child, so here, this 5, if it has a left child, then we need to add it to our graph, right? So if node dot left, we're going to say, okay, we're going to put into the graph node.val. And the reason that we're going to use node.val here instead of just node is because our start values are actually given as integers, which is going to represent the value of that node. If they were given to us as the actual nodes, then we would put it as node.val, but we need to use node.val instead of node in this case because we're working with the integer values, not the actual node objects itself. So we're going to say, we're going to add to the graph. So from this particular node that we're at, so this 5, we can reach the 1, right? So we need to append to our items for that particular node. We're going to say, node.left.val. So for the left child, we can reach the parent, right? So we're going to put into there the fact that we can reach, the current node that we're at, which is going to be node.val, because remember, we're putting the values into our dictionary, not the node objects themselves. So we can reach the node with, whatever its value is, and it's going to be its parent. So to reach it, we would have to go up. And we can do the opposite. We can say graph of node.val, and we can reach, that left child. So we're going to say node.left.val, and we're going to put that we can reach it by going left. Now we still need to process the left child, so we're going to add it to the queue. So we're going to say add node.left. And here we're in the queue, we're actually working with nodes because we need to access these, dot left and dot right properties. So that's why we put the nodes in the queue, but we're working with the values in the graph itself. A little bit confusing, but it's just one of those problems because the start and end are given to us as integer values and not the actual nodes themselves. So we've done that for the left child. Now we need to do the same for the right child. So we're going to say if node.right, then we need to update our graph again. So from that right child, remember we can access the parent. So we're going to be adding, the current node value, and it's going to be accessible by going up. And then we can do the same for the node, and that we know that we have its right child available to us. So we're going to say node.right.val, and we access it by going right. And remember, we still need to process that that node. So we're going to say node.right, add it to the queue, and that's going to be it for the actual building of the graph. Now what we need to do is we need to start our BFS from the start value and look for this destination value while keeping track of the path. So we're going to set up another queue, and remember it has to be a queue because we're doing a breadth first search, because BFS will give us the shortest possible path in this undirected graph that we have. That is a property of undirected graphs, is that if you do a BFS over them, you will get the shortest path from one node to another. So let's set up another queue. So we're going to say collections.dec, and this time we want to initialize it with our start value, and also we're going to be keeping track of the current path that we've been on, and we're going to use a string to denote this. In Python, strings are mutable, and you can actually append to the end of a string in constant time. Other languages may not have this available, so you might want to use a string builder here to do that, because I think, what is it, in Java and C++, you can't actually, strings are immutable, so you can't modify them, but in Python you can. So that's what I'm going to be doing here. So we have our queue, and we start it with the current node that we're at, and then the current path that we've taken. And remember that we need a scene set to basically make sure that we don't get caught in an infinite loop, which obviously we would just go on forever and we would never return our solution. And we are actually guaranteed to be able to reach our solution, so we don't have to worry about the case where we don't reach it, because I guess the destination is not in the tree. So we will be able to find an answer. So now we just need to do the BFS. So we're going to say while queue, we're going to say that the current value that we're at, remember we put the values into the graph, not the nodes. So we're going to say the current value and the current path is going to be equal to, we're just going to pop from the queue, and that's what is going to be at the top of the queue. Now, if the current value is, if it's in scene, then that means that we've already been to this node, and we want to just skip over this part because we'll get caught in an infinite cycle if we actually process this node. So we'll just continue, which will just push us one iteration further in the queue. Otherwise, we want to add that we've seen this node to make sure that we don't get caught in those infinite loops. And then what we want to do is we want to say if the current value is equal to the destination value, that means that we've reached our destination and we have our solution now, because we will have found that shortest path, because when we arrive at destination value, we know that it's the shortest path, because again, we're using a BFS. So all we can do here is actually just return the current path, which will represent the path that we've taken so far to get to this point. Otherwise, we need to process all the possible paths from that node. So we're going to say for child direction in graph of current value. So that's going to be all the possible directions, right? For 5, right, we have the direction we could go left, or we could have the direction that we go right. And what we could do here is we can say q the append. So we're going to append to our queue all the possible options. So child cur path. So that's going to be the string representing the current path, and we're going to append to the end of that the direction that we need to go in. Remember, we stored it as U, R, or L, and that will give us our, the next, what the next path would be if we took that child. So this is how we're going to solve this question. Let's submit it, make sure that it works, and it is a little bit of a slow one because some of the test cases are absolutely massive. But we should be able to solve it. And I just want to check here that we could potentially make one optimization. We're going to say if child not in scene. This could actually speed things up. Let me just make sure. That could be a little bit of an optimization to make sure that we don't add anything to the queue. Okay, yeah, so it does bring the time a little bit slower. So if we actually just check whether or not the child is already in scene, then we don't have to add it to the queue. So it should bring down our speed a little bit lower. So what is the time and space complexity of this question? Well, what are we doing? In the first part, we are building a graph to represent our tree, in a different format. So to do that, it's going to take big O of n time because we have to process every single element in the tree. Then what we're going to do is we're going to basically do a BFS across our tree from one node to another. And remember, a BFS is going to be, big O of n runtime complexity. Because in the worst case, think about a tree that looks like an inverted V, right? So it'd be like something like this. You could start at the bottom here and you'd have to go all the way up and then all the way back down to the right. So you'd have to touch every single element. So that would be big O of n. So asymptotically, this is still just going to be a big O of n solution. What is the space complexity? Well, the space complexity, we basically just need to define a graph, which is going to represent our, tree as a graph. So this is going to be big O of n because we're just taking all the same data from, the original tree, but we're representing it as a graph. So it's going to be big O of n. The queue will be big O of n because we need to, process all the nodes. But obviously we get rid of this queue once we override it with this one, but this one is also going to be, in the worst case, a big O of n. So much like the time complexity, our space complexity is also going to be big O of n, because essentially what we're doing is just BFSing over a graph. So the time complexity is big O of n, and the space complexity is also big O of n. And that's really the best that you can do here. There's really no way to bring that down. And I think just the speed here is because some of the test cases are absolutely massive. So yeah, there's really not much you can do there. I'm sure there might be some smaller optimizations, but in the end, the runtime is still big O of n and the space is still big O of n, because you need the queue to do the processing and you also need the graph. So that's going to be how you solve this problem. This is quite an interesting one. I really like these questions where you have to transform a tree into a graph. I think it really demonstrates your knowledge of both graphs and trees. And for some reason, I just really like tree and graph based questions. I think they're really fun and quite easy and intuitive. So hopefully, this question made it, simple for you to understand how to solve this one. And if you enjoyed it, please leave a like, comment, subscribe. If there's any other videos you'd like me to make, please just leave them in the comment section below. I'd be happy to make these videos for you guys, whatever you want. I'm here to help you guys get, good jobs in FAANG. So anything you need to help you in your preparation journey, just let me know and I'll be happy to help. Otherwise, have a nice day and happy coding. Bye.